This is a Unit 4 practice exam for Math 1050. So we have a system of equations here. One's linear, this one is not linear. So we're going to solve this one using elimination. You can see we have like terms on x variables. We do not have like terms here on y, but we do have like terms with x. So if I multiply this bottom equation by -2, then you can see we have opposite coefficients of x. So when we try the elimination method now, the x variables eliminate. Notice that y is not like terms y squared and 2y, so when you add those together, they need to be added together as y squared plus 2y equals 0. Now we have a quadratic equation. If we factor out a y, now we can solve for y equals 0 and y equals -2. Now remember, when we're solving a system of equations, we're looking for the point or points on the graph where these two graphs intersect. So we have the y values, we need the x values. And since we have two y values, we need to solve for two x values. So when y is equal to 0, I'm going to use this bottom equation here because it's linear to solve for x. So when y equals 0, we have 3x minus 0. Instead of subtract y, I'm going to subtract 0 because y equals 0. And that's equal to 5. So x equals 5/3. When y equals -2, I'm going to use the same equation, 3x subtract y, so that's going to be subtract -2. So x equals 1. So the other solution is 1, comma, -2. And we have three equations and three variables. So what we're going to do is choose two of the equations and eliminate one of the variables. So I notice here we have 2x and -2x. So if I take the top equation and the bottom equation, and eliminate the x variable, that leaves y minus 3z equals -1. Now since there's two variables there, we're going to have to repeat this step with two of the other equations. So if I take, for example, the top two equations here, and multiply that equation there by -2, then what we'd end up with is, again, we can eliminate x, and it's important. In step 1 here and step 2, you have to eliminate the same variable. So then we end up with y minus 3z equals -1. So step 3 of this process is you take the result from step 1, you take the result from step 2, and you form a new system of equations. You can see here already, though, that the result from step 1 and the result from step 2 are identical equations. Usually it's not, which means you could solve for one of the other variables. In this case, since they're identical, if we try to do elimination method, for example, what we'd end up with is the variables cancel, constants cancel, so we have 0 is equal to 0, which is an indication of infinitely many solutions. So what we talked about in class, if there's 3 variables, meaning in this case x, y, and z, the convention in most college algebra textbooks is to let z equal t. T is a parameter. The parameter t can be any real number. So if we let z equal t, now we can go back up to this step, step 3, and take one of the equations to solve for y in this case, because we know the value of z. So we can solve for y. So then y minus 3, instead of 3z, I'm going to call that 3t. And then if you add the 3t to the other side, we get y equals 3t minus 1. Now we can use one of the original equations that have the 3 variables. I'm going to use this middle one. So x minus y plus z equals 2. That becomes x minus, I'm going to substitute y as 3t minus 1. And whenever you make a substitution, remember, especially if the substitution involves several terms, you do that substitution in a parenthesis. And then plus z becomes plus t. That equals 2. Now I'm going to get rid of the parenthesis by distributing this negative sign. And now we're solving, I'm going to solve for x, so I need to get all of these terms on the other side of the equal sign. Negative 2t just came from combining the like terms, negative 3t plus t. So I'm going to add the 2t to the other side and subtract the 1. So x equals 2t plus 1. So now my solution x comma y comma z becomes, for x we have 2t plus 1, for y we have 3t minus 1, and for z we had t. Question 3, we're going to solve again a system of equations involving 3 variables, but this time we're not going to use elimination method. We're going to use what we learned in section 6.3 called elementary row operations using an augmented matrix. So the first step here would be to create the augmented matrix. And remember the process is this needs to be a 1, then we want a 0 here and a 0 here. And then once that's complete, then we want a 1 here and then a 0 here. So we already have a 1 in the top left corner, so I need to get this to be a 0 and get that to be a 0. So I'm going to multiply row 1 by negative 2. Then we're going to add that to row 2 to create a new row 2. So this means everything in row 1 is going to be multiplied by negative 2. So this makes negative 2 plus 2, which is 0. Negative 2 times here makes negative 4, plus negative 1 is negative 5. Negative 2 times negative 1 is positive 2, plus 3 is 5, and then negative 2 times 6 is negative 12, plus negative 13 is negative 25. Now I also want to have a 0 right here, so if I could make this negative 3 plus that 3 would make it 0. So now I'm going to do a new row operation, negative 3 times row 1. Now I'm going to add that to row 3 to create a new row 3. So now row 1 is going to be multiplied by negative 3. Every entry in row 1 will be multiplied by negative 3, and then you add it to row 3. So 1 times negative 3 plus 3 is 0. 2 times negative 3 is negative 6, plus negative 2, negative 8. Negative 3 times negative 1 is 3. 3 plus 3 is 6. And then 6 times negative 3 is negative 18. Negative 18 plus negative 16 is negative 34. Now I want to get a 1 right here. So if I multiply row 2 by negative 1/5, that's going to make a new row 2. So I'm going to write that over here to save some space. So that's going to be 0 times negative 1/5 is 0. Negative 1/5 times negative 5 is positive 1. 5 times negative 1/5 is negative 1. And negative 25 multiplied by negative 1/5 is positive 5. Now the last thing, well, towards the end, we want to get this to be a 0. So if I multiply this row by 8, that's going to put an 8 right here. 8 plus negative 8 is 0. So I'm going to do row 2 times 8. So 8 times row 2. I'm going to add that to row 3 to make a new row 3. So the entire row needs to be multiplied by 8. Starting here, 0 times 8 is 0. 0 plus 0 is 0. 1 times 8 is 8, plus negative 8 is 0. Negative 1 times 8 is negative 8, plus 6 is negative 2. And 5 times 8 is 40. 40 plus negative 34 is 6. So now we can take this bottom row and make an equation. Negative 2z equals 6, therefore z equals negative 3. Then we can take this middle row and create an equation y minus z equals 5, and we can replace z with y minus negative 3 equals 5, so that's y plus 3. If you subtract 3, you get y equals 2. And now that top row is the equation x plus 2y minus z equals 6, which we can turn into x plus 2 times y minus z equals 6. So this is 4 plus 3, that's 7. X plus 7 equals 6, which means x equals negative 1. So the solution to our system of equations here is x equals negative 1, y equals 2, and z equals negative 3. Now when you're trying to multiply matrices together, you need to check the dimensions. For part A, for example, matrix A is a 3 by 3, and matrix B is a 2 by 3. Because these two numbers here don't match, part A is not possible. Now for part B, we're going to do matrix B times matrix A. So matrix B well, I guess we should check first. Matrix B is a 2 by 3, and matrix A is a 3 by 3. So the inside numbers there, they match. So the multiplication is possible. And the multiplication is going to result in a 2 by 3 matrix, which I'm going to write there. So this entry here is going to be a combination of this row and that column. So 1 times 0 is 0, plus 0 times 2 is 0, plus 5. So 0 plus 0 plus 5. This entry is a combination of that column with that row. So 0 times 1 is 0. 2 times 3 is 6. 1 times 0 is 0. So 0 plus 6 plus 0 is 6. This entry is a combination of that column and this row. So 0 times negative 1 is 0. 2 times 1 is 2. 1 times negative 2 is negative 2. So 0 plus 2 plus negative 2 is 0. Now, this entry is a combination of that row to that column. So 3 times 1 is 3. Negative 2 times 0 is 2. Or 0 rather. And 4 times 5 is 20. So we have 3 plus 0 plus 20. So 23. This entry is this column with this row. So 3 times 1 is 3. Negative 2 times 3 is negative 6. And 4 times 0 is 0. So 3 plus negative 6 plus 0 is negative 3. And finally, we have this entry combining this row to that column. So that makes negative 3. That makes negative 2. That makes negative 8. So negative 3 plus negative 2 is negative 5. Negative 5 plus negative 8 is negative 13. So this matrix right here is the product B times A. Now for part C, we're going to do 2 times matrix B. Well, let's check first. When we're adding or subtracting matrices, even if they're multiplied by a constant value there, we have to have equal dimensions of both matrices. So B is a 2 by 3, C is a 2 by 3, so we can subtract them. So 2 times B minus 3 times C so this is called scalar multiplication. We're just going to multiply every entry in B by 2. And then multiply all the entries in matrix C by 3. And then subtract. So 0 minus negative 9 is 9. 4 subtract 6 is negative 2. 2 subtract 12 is negative 10. 6 subtract negative 3 is 9. Negative 4 subtract 0 is negative 4. And 8 subtract 21 is negative 13. Question 5, we're going to use an inverse matrix to solve a system of equations. So the first step, if you recall from section 6.5, was to create the matrix equation. So we have the coefficient matrix, a matrix containing the variables, and then a matrix containing the constant 10 and 30. So we're solving for x and y. It's being multiplied by this matrix, so we need to cancel this matrix so that x and y can be isolated. So what we need to do is multiply by the inverse matrix here and that same inverse matrix here. So we got to find the inverse of matrix with this matrix. So if I'm going to call this here matrix A, then the inverse of A is 1 divided by A times D, so that's negative 8, minus B times C, so that's negative 9. And then remember A and D change places. And B and C, they don't change places, they switch signs. So that becomes a positive 3, that becomes a negative 3. So here in the denominator, negative 8 plus 9 is 1. So there's the inverse. So what we do now is we take this inverse, we multiply it here. So if I multiply the inverse of a matrix to itself, those cancel out. So the next step here is to take this inverse and multiply it on the left side of this matrix. So I'm going to take this inverse and multiply it by this matrix here. And find the product right there. So this entry is a combination of that row to that column, so that makes negative 20. This makes 90, so 90 plus negative 20 is 70. Now here we get negative 30 combined with 120, so that's 90. So this matrix 70 and 90 is equal to that matrix, which means the solution is 70 for x and 90 for y. Now part B is the same process as part A, but when you have 3 equations and 3 variables, you have to find the inverse of a 3 by 3 matrix, which is very lengthy and rather difficult, to be honest. And so for a problem like this, the inverse matrix will be included in the problem. So we're going to use this inverse matrix. So we still have our matrix equation. We have a matrix containing the variables, and then a matrix containing the constant values after the equal sign. So this matrix is multiplying x, y, and z. So we need to solve for x, y, and z, which means this matrix needs to be isolated. It's being multiplied by this matrix. The only way to cancel a matrix is to multiply it by its inverse. This is the inverse of this matrix. If this weren't given, we would have to find the inverse. And like I said, the inverse of a 3 by 3, to find that is a very lengthy process. So this times this means that this matrix will disappear. We also have to multiply this inverse on the left side over here. And that's what we need to show on this problem, is this matrix multiplied by this matrix, which is going to give us the values of x, y, and z. Okay, so this entry is a combination of that row and that column. So this makes -5, that's -6, and that's +5. So -5 plus -6 is -11, plus 5 is -6. Now here we're going to combine this row to that column. So 2 times 1 is 2, 1 times 3 is 3, and -2 times 1 is -2. So we have 2 plus 3, which is 5. 5 plus -2 is 3. Finally, we have this row to that column, so that makes -4, makes -9, that makes +5. So -4 and -9 make -13. -13 plus 5 is -8. So what we have here is this -6, 3, and -8 matrix is equal to our XYZ matrix, which means the solution is x equals -6, y equals 3, and z equals -8. All right, in section 6.6, we learned about determinants of a matrix and Cramer's rule. Cramer's rule uses determinants to solve a system of equations. So when you have two equations and two variables, we need three determinants. We need determinant D, which is the determinant of the coefficients. So that's 3 times 4, which is 12, minus 5 times -2, which is -10, which is 22. The next determinant, D sub x, the subscript x means the values in this x column are going to be replaced with those constant values. So instead of this 3 and 5 in the x column, we're going to have -1 and -31. And then the values in the y column stay the same. So this determinant is -1 times 4, which is -4, minus -31 times -2, which is 62. So -4 minus 62 is -66. And then the final one is d sub y. So now the subscript y means that in the y column, we're going to replace these values with these values. So -1 and -31 go in the y column. The x column stays the same as it originally was, 3 and 5. So now this determinant is 3 times -31, which is -93, minus 5 times -1, which is -5. And here we get -88. So those are the determinants. Now Cramer's rule now uses these determinants to say the value of x is the determinant d sub x divided by d. So that's -66 divided by 22, which is -3. And then y is equal to determinant dy divided by d, which is -88 divided by 22, which is -4. So our solution here is x equals -3 and y equals -4. Part B, we are going to use Cramer's rule again. If you have three variables and three equations, you need four determinants. However, this one says we only need to solve for x. So since x is equal to d sub x divided by d, then we only need those two determinants. So first we need d determinant, which is just the determinant of all the coefficients. Now in class, there were two different ways presented to find the determinant of a 3 by 3 matrix. You can use either way. I'm going to use this method where these first two columns are copied to the right side over here. We have 3, 4, 1, and 2, -1, -3. Now, these three values multiply together, these three right here. So that product is 12. The product of these three numbers is 2. And the product of these three numbers, -8 times -3 is 24. Now, we're going to go this direction. The product of these three numbers is 2. The product of these three numbers is -9. And the product of these three numbers is -32. So the way this works now is these three numbers add, these three numbers subtract. So it's 12 plus 2 plus 24. Then we subtract the ones in blue, so that's -2 minus -9 and minus -32. So that determinant is 77. So now for this determinant, we're going to take the values here, 10, 5, and -1, and that's going to replace the x column. All others stay the same. And then I'm going to use the same method here, so I'm going to copy these two columns over here. And then in that diagonal, 10 times -1 times -4 is 40. In that diagonal, we get -2, and in this one, we get -10 times -3, which is +30. In this diagonal, we get -2. In that one, we get -30. In this one, we get -40. And we have 40 plus -2 plus 30 minus -2 minus -30 minus -40. So 40 plus -2 is 38. 38 plus 30 is 68. Plus 2 plus 30 plus 40. So that's 70 plus 30, it's 100. That's 140. So then coming back up here, x is equal to the determinant d sub x, so that's 140, divided by determinant d, which is 77. So that means x is equal to 140 divided by 77, which is 1.81. Repeating. Question 7 is from section 6.7, finding the partial fraction decomposition. There were a few different instances of partial fraction decomposition depending on the factors of the denominator, whether they were repeated or whether they were linear. These are both linear, non-repeating. So since there's only two factors in the denominator, we're going to have two partial fractions. And then if this whole equation was multiplied by the common denominator, x minus 3x plus 5, then we'd have 9x minus 11 equals a times x plus 5 plus b times x minus 3. So now the process that was shown in class involves choosing convenient values for x, because if we only have one equation but we have to solve for two variables, we have to eliminate variables. So if x was negative 5, for example, negative 5 plus 5 is 0, so that eliminates a. So since we have two variables, we're going to have to do this twice. For the first one, I'm going to let x equal negative 5. So here this makes negative 45 minus 11, that's negative 56. Here a is eliminated because this makes 0. Negative 5 minus 3 is negative 8 times b is negative 8b, so then b is equal to 7. So we already solved for b, now we need to solve for a, which means I have to eliminate b. So if x was 3, then we have 27 minus 11, that's 16. 3 plus 5 is 8 times a is 8a. And then b is eliminated because 3 subtract 3 is 0. So this means here a is equal to 2. So now we have the values for a and b. So 2 divided by x minus 3 plus 7 divided by x plus 5. Now we're getting into chapter 7, sequences and series. So on question 8, we just need to find the first four terms. And we have, here in part A, we have an explicit formula, and in part B, we have a recursive formula, both of which were talked about in section 7.1. So in an explicit formula, the first term is found by letting n equal 1, the second term is found by letting n equal 2, and so on. So a sub 1, the first term would be when n is equal to 1, so 1 subtract 1 is 0, 2 to the 0 power is 1, 1 times 2 is 2. The second term would be when n equals 2, 2 subtract 1 is 1, 2 to the first power is 2, 2 times 2 is 4. Third term was when n equals 3, 3 subtract 1 is 2, 2 to the second power is 4, 4 times 2 is 8. And the fourth term, 4 subtract 1 is 3, 2 to the third power is 8, 8 times 2 is 16. So the sequence is 2, 4, 8, 16, as far as the first four terms are. Now for a recursive sequence, or recursive formula rather, we already know that the first term is 2. The second term, when n equals 2, here n equals 2, 2 subtract 1, so this is the first term, which is 2, plus 5 is 7. The third term, when n equals 3, n equals 3 minus 1, that means a sub 2, that's the second term, which is 7. 7 plus 5 is 12. For the fourth term, when n equals 4, we have here 4 minus 3, or 4 minus 1 is 3. A sub 3 means the third term, which is 12. 12 plus 5 is 17. So we have 2, 7, 12, 17 for the first 4 terms. Question 9, we're finding an explicit formula. What we practiced in 7.1 was first determine whether the sequence is geometric or arithmetic. And it depends on whether you're adding a common difference or multiplying by a common ratio between terms. So here we have negative 11 to 19 to 49 to 79. So it looks like we're adding 30. So this plus 30 plus 30 plus 30. So since we have a common difference d, it means this is arithmetic. And there should be, there we go. So this is arithmetic. Which means we need to find a common difference. So d equals 30. So a formula, an explicit formula for the nth term, the formula that was given in class was first term plus n minus 1 times the common difference. So the first term is negative 11, and then the common difference is 30. And if we simplify that expression, negative 11 plus negative 30 is negative 40 minus 41. So 30n minus 41 is an explicit formula for the nth term. Now for part B, to go from negative 3 to negative 12 to negative 48 to negative 192, looks like we're multiplying by 4. Since we're multiplying, that makes this geometric. And the common ratio is r equals 4. Now the formula for a geometric, an explicit formula of a geometric sequence is first term multiplied by the common ratio raised to the power of n minus 1. So we know the first term is negative 3. Common ratio is 4, and that's raised to the power of n minus 1. So in part A, important thing they're telling us here is that this sequence is arithmetic, which means between these terms, we're adding a common difference. So if you recall, the discussion we had in class was an arithmetic sequence is relatable to a linear function, and a linear function has a constant rate of change. In other words, a slope. So the example problem we did that was similar to this one, one way we can think about a sequence to relate it to a linear function is to make an input and output table. When n is equal to 15, a sub n is equal to 53, and when n is equal to 33, a sub n is equal to 89. A slope, remember, is a change in y values, which in this case is 36, divided by a change in x values, which in this case is 18. So then difference in y divided by difference in x is 36 over 18. So the common difference, 36 over 18, the common difference between individual terms is 2. So we're adding 2 to each term. So we know then that an explicit formula for this arithmetic sequence is 2 times n, since the common difference is 2, but we don't know this value that we're adding. And what we're doing here, again, is relating an arithmetic sequence to a linear function, linear meaning y equals mx plus b, where x can be replaced with n and y can be replaced with a sub n, just like we did here, which means the slope is just the common difference. M is, so we're just missing this value for b. That's what we're doing here. We're just relating an arithmetic sequence explicit formula to a linear function y equals mx plus b. Well, we have one equation with 3 unknowns. We don't know this value, n or a sub n. But if we replace n and a sub n with one of these known values, then we could solve for this unknown value. So n could be 15 and a sub n could be 53, for example. We could solve for that unknown value. So 2 times 15 is 30. If you take 30 from 53, we get 23. So the explicit formula for this nth term is 2n plus 23. So if I want to find a sub 10, the 10th term, that means n is 10. And I want to find that 10th term. So if n is 10, so the 10th term is 2 times 10 plus 23, which is 43. Now for part B, there was no explanation as to what kind of sequence this is, other than it's giving us R, which is a common ratio. So this implies that this is a geometric sequence. R meaning common ratio. And we already have the first term. So with the information given, we can make an explicit formula for the nth term, which is first term times common ratio raised to the power of n minus 1. So then a sub 4 would just be replacing n with 4. So 4 minus 1 is 3. Okay, question 11. All parts, part A through part E, is from section 7.2. Partial sum of arithmetic and geometric sequences, and if possible, an infinite sum of a geometric sequence. We'll get to that in part E. So for part A, we have a partial sum, and we know this is a partial sum because it has a beginning and an end, so it's a partial. So then we know how to decide, is it a partial sum of an arithmetic or a partial sum of a geometric series? So it depends on if we're multiplying by the same value to get from term to term, or if we're adding. So 38 to 46 to 54 to 62 looks like we're just adding 8 to go from term to term. So this is a partial sum of an arithmetic series. So the formula given for this was half of the numbers being added together, and then take the first term and add that to the last term being added. So we know the first term being added is 38 and the last term is 302. What we don't know is how many terms are being added together, how many terms are in between here. That's n. So what we need to do is create an explicit formula for this sequence. And since it's arithmetic and it has a common difference of 8, we can use the formula to find the explicit formula for an arithmetic sequence. So the first term is 38, and the common difference is 8. So what we can use this for is 302. What we're trying to find is what spot in the sequence does that occupy. For example, this is the first n equals 1, this is n equals 2, this is n equals 3, this is n equals 4. What is this? Is it n equals 50, n equals 15? So since we don't know the n value, that's what we're solving for, but we do know that whatever this n value is, the a sub n value is 302. So we can put 302 in for a sub n and simply solve for n. So 272 divided by 8 is 34. Now again, what this means is this is in the 34th spot of this sequence. So from 1 to 34, that means we're adding 34 terms together. So now we can use this partial sum formula. 34 divided by 2, the first term in that partial sum is 38. The last term in that partial sum is 302. So this is 5,780. So this symbol means summation, so we're adding 13 terms, and the 13 terms are going to come from the sequence. Now 6n minus 14 is linear, which means this is a sequence. This is a formula that describes an arithmetic sequence. So this is a partial sum of an arithmetic sequence. So it's going to use the same formula, half the number of terms multiplied by the sum of the first term plus the last term being added. Now we know that there's 13 terms, so n equals 13, but we got to find the first term being added and the 13th term from that formula. So the first term is just going to be when n equals 1. 6 times 1 is 6 minus 14 is negative 8. So the first term is negative 8. The 13th term is going to be 6 times 13 minus 14. And that's 64. So now we can use this formula. N divided by 2 is 13 divided by 2 times negative 8 plus 64. So this is 6.5 times 56, which is 364. Now we need to do something similar for part C, but first we have to decide, well, it's a partial sum because, again, it has a beginning and an end, but is it the partial sum of an arithmetic or is it a partial sum of a geometric series? So we have to decide based on the terms, 1 to 4 to 16 to 64. Looks like each term is being multiplied by 4, and then there's a bunch of terms in between to end up with that one. So then the partial sum of a geometric sequence has a different formula. In the numerator, we've got first term, a sub 1, and then this expression is 1 minus the common ratio raised to the power of n, and that n here, remember, is the number of terms being added, which at this point we don't know. And then the denominator is 1 minus the common ratio. Now we know the common ratio is 4, and the first term is 1, obviously, but what we don't know is how many terms are being added. So we need to, like in part B, create an explicit formula for the nth term. So for a geometric sequence, the explicit formula is first term times the common ratio to the power of n minus 1. So what we need to figure out is this 65,536 goes in place of a sub n so that we can find out what spot in the sequence it's in, the n value. So we replace a sub n with 65,536. So what we have is an equation that we can solve. Now this, we're going to have to think back. This is a variable that's in the exponent. You can't solve for a variable that's in the exponent unless we can cancel the base. So we have to use logarithms to solve this equation. So we're going to divide by 1 on both sides, which just leaves 65,536. And then we do a log base 4. So if we do a log base 4 on both sides, then that will cancel the base 4. So then we have n minus 1 equals log base 4 of 65,536. And then if we add 1, we get n equals log base 4, 65,536 plus 1. Now, remembering back from the last unit, log base 4, most calculators can't do, so we're going to have to use a change of base formula, but this is definitely something that you would do on a calculator. So change of base formula just means log of 65,536 divided by log 4, which turns out to be 8. So n equals 8 plus 1, which means n equals 9. So this is the 9th term. So we have the first, second, third, fourth. There's 5th, 6th, 7th, 8th terms in here somewhere, and then this is the 9th term. So we're adding 9 total terms. So this is the value of n. So now we have enough information to use this formula. First term is 1. 1 minus the common ratio raised to the 9th power divided by 1 minus 4. And again, this is going to be something that you would do on a calculator. And you would get 87,381. For part D, we have a partial sum because we started the first term and ended the 8th term, so this is a partial sum. And this is the explicit formula for a geometric sequence. So we're doing another partial sum of a geometric sequence, which means we're going to use the same formula as from part C. So the sum is equal to the first term is 1 minus r to the n divided by 1 minus r. Now the explicit formula for a geometric sequence means that this is the common ratio. So r is 3. First term is negative 2. Or if you forget, you can always find the first term by plugging in a 1. For I, 1 subtract 1 is 0. 3 to the 0 power is 1. 1 times negative 2 is negative 2. So we get negative 2 as the first term. And the number of terms we're adding together is 8 because we started the first term and end at the 8th term. So again, we have all the information we need. And then you would use a calculator to figure out that. And it turns out to be negative 6,560. For part E, we have an infinite sum because we're starting with the first term, but we keep adding an infinite number of terms. So if you remember from our discussion in section 7.2, the infinite sum is only sometimes possible, and only if it's a geometric series. So this is the explicit formula for a geometric series because it's an exponential. And then the other, so there's two, remember there's two things. It has to be a geometric series, and the common ratio has to be between -1 and +1, which 1/2 is. So r equals 1/2, and the first term is 3. Those are the two things you need for the formula for the infinite sum of a geometric series, which is first term divided by 1 minus r. So the first term is 3. Common ratio is 1/2. 1 subtract 1/2 is 1/2. 3 divided by 1/2 is 6. And finally, question number 12, we're expanding this binomial expression. This is from section 7.3. So there were two different ways to figure out the coefficients of the expansion. One was using Pascal's triangle, the other was using the binomial theorem. I'll show you both ways here. So to get the coefficients for each of the terms, first we're going to do Pascal's triangle. Now if it's raised to the 4th power, we need 5 rows of Pascal's triangle. So these are the coefficients. 1, 4, 6, 4, 1. Now if you don't want to do Pascal's triangle, the other way is to do the binomial theorem. So we could do 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. Now these you could do by hand, but it's just easier if you use the functions on your calculator. So 4, choose 0 is 1, 4, choose 1 is 4, 4, choose 2 would end up being 6, 4, choose 3 is 4, and 4, choose 4 is 1. So either way, if you use Pascal's triangle or if you just use the binomial theorem to get your coefficients, it's going to give you the same numbers. Now we're ready to expand this binomial. So for the first term, we're going to take the first coefficient and then the first term raised to that power. So it's going to be 1 times 4a raised to the 4th power. For the next term, it's going to be this coefficient, this term raised to the 3rd power, and this term raised to the 1st power. So there's going to be 4, and then 4a is raised to the 3rd power. Then we're going to multiply negative 3b to the 1st power. Remember what we talked about in the discussion, that the sum of these two exponents has to equal the original exponent. Okay? This 4, remember, came from that coefficient. Now the next term can have a coefficient of 6, and then the first part of that binomial 4a is going to be raised now to the 2nd power, and then the negative 3b is going to be raised to the 2nd power. The next term is going to have a coefficient of 4, then 4a is raised to the 1st power, negative 3b is raised to the 3rd power, and finally the last term has a coefficient of 1, and we only need this term, negative 3b, so it's 1 times negative 3b raised to the 4th power. Okay, now we simplify each term here. So 4a raised to the 4th power is 4a times 4a times 4a times 4a. So 4 times 4 times 4 times 4 is 256. And then 256 multiplied by 1 is still 256. And then a to the 4th. Now the next term here, going to do exponents first. So 4a to the 3rd power is 4a times 4a times 4a. So 4 to the 3rd power is 64. And then, so I'm going to write 64 here. This is 64a to the 3rd. Then we're going to multiply that by 4. Then we're going to multiply that by negative 3b. So then we need to do 4 times 64 times negative 3. 4 times 64 times negative 3 is negative 768. So minus 768, a to the third, b to the first power. Now, the next term, we're going to have 4a to the second power. So 4a times 4a is 16a squared. And then negative 3b squared is negative 3b times negative 3b, so that's 9b squared. And that's multiplied by 6. So the coefficient there is going to be 6 times 16 times 9, which is positive 864. So plus here, plus 864. Then we have an a squared and a b squared. Now here we have 4a to the first power, which is 4a. And then negative 3b to the third power is negative 27b cubed, and that's multiplied by that 4 there. So the coefficient for that term is going to be 4 times negative 27, which is negative 432. And then we're going to have an a to the first power and a b cubed. And then finally, we have negative 3b to the fourth power. So negative 3 to the fourth power is positive 81. Times 1 is still positive 81. So it's plus 81 times b to the fourth.